And it looks like we're live. Let's audio stream is going in. Preview is there. Let's see if sound is coming in. Yep, it does seem to be sound coming in. Perfect. And according to my clock here, still got 10 seconds before 7 a.m. All right. Well, happy Wednesday, middle of the week. It's I'm a bit tired today because last night there was a sort of happy hour meetup in Denver, and ended up going to that and then meeting a whole bunch of awesome people in the community. But that's also always at a bar, and it's a happy hour. So there's that. Anyways, so let's see where we're at. Also, if you're hanging out in the chat or you're watching this in a VOD, leave a comment, say hi. Always happy to see like who's watching these videos and if you're getting anything out of them. Okay, so let's open up new browser window and let's go to the book. Second edition. Ooh, we were on chapter 7, right? And let's also open up our terminal and go find out exactly where we were. So, projects mine, learning Rust. Okay, well, no, we were at chapter 8.1, updating a vector. So let's go check that out. So 8.1 vectors, updating a vector. Okay, right. So the last we saw was that there's this we're being introduced to another I want to say data storage way, but another data structure that will allow us to like store data. Specifically, it's feeling like an array, but a vector is really just like a series of numbers. And I'm used to thinking of vectors as like a single, a 2D vector, which is, for example, X and Y on a grid, or a 3D vector, X, Y, and Z. I don't think I've ever used anything bigger than that, so that'll be interesting. I've also don't think I've ever thought of data structures as like array type things as vectors, even if they're exactly the same type of data, if I'm not making a game. Simply because that's just how I think of vectors as part of making games. So this will be fun to sort of like change my mental model about programming and adding this into like just the normal data types. Okay, so with that, let's continue on and sort of like see what we can see here. Updating a vector. To create a vector and then add elements to it, we can use the push method as shown in listing 8.3. So they have let mut equals v equals vector new. So they're creating a new vector. So this is like the third way to create a vector, I believe. And then you can push data. And my guess here is because all the data has to be exactly the same type, the first push is going to define what type this vector can take in. So I want to sort of test that out a little bit. So let's also, all my controls are, there we go. Let's create one to the right like this. And we're going to go into chapter 8, vectors, and open up code. Okay, so specifically in here, oh, apparently I did not. Okay, there's a dot readme. Oh, that's okay, never mind. That's the swap file from from Vim. I should turn off swap files so it doesn't show up, or like hide them or something. Okay, so here we go. This doesn't work. It needs the type annotations. So vec new. This does work, but it's saying this won't. But is it won't because I'm not also pushing into it? So how about like my ints equals vec new, and then immediately after that I can say my ints dot push, and then we're going to put in like 1. Cannot borrow a mutable local variable my ints as mutable. So let's go see what I did wrong here. Oh yeah, mute. I have to mute it. So that mute. Wow, it didn't even complain that I'm not using it. I'm storing it, but I'm not actually accessing this data. Maybe, I mean, it should be able to tell if it really wanted to. Maybe it's just the code. Okay, so this works. My ints.push. Now, of course, if I try to do like a 1.0, it will complain bitterly because this is that's a float, and we can't do floats. It's expecting integers. Now, can I print this out? Like, does it have a debug on it? So if I say print line, we'll save this. Let's go try to run it. So I think I'm going to quit out of here. Chapter 8, vectors. I don't need you anymore. Okay, so let's cargo run. Okay, so default formatter won't work. Let's try the debug formatter. And here it does work. So it does have a debug formatter that we can use to sort of like inspect our vectors and see what's inside of them, which is this this list essentially of what we pushed in the order. All right, let's get back to the book. As with any variable, as discussed in chapter 3, if you want to be able to change its value, we need to make it mutable using the mute keyword. The numbers we place inside are all of type i32, and Rust infers this from the data, so we don't need the vec i32 annotation. Dropping a vector drops its elements. Like any other struct, a vector will be freed when it goes out of scope, as annotated in listing 8.4. So we have this block here. So let v equals new vector, we fill it with some data, and then this vector, its position in memory is destroyed and freed for the operating system. When the vector gets dropped, all of its contents will also be dropped, meaning those integers it holds will be cleaned up. This may seem like a straightforward point, but can get a bit more complicated when we start to introduce references to the elements of the vector. Let's tackle that next. Before we do that, I sort of want to explore that, sort of see if I could see what that means. So I'm also going to annotate this by saying this works because we are pushing, and therefore Rust can figure out what goes inside. Okay, so now for down here, I want to say, I want to create a vector and store like some stuff inside. So if I have let my number equals 55. So currently main will own my number. Now if I pass this to a function, then the function will own it. So let's create a, well, I guess I don't want to do a function. I want to put it inside a vector and see, does the vector own it? If I pass it in fully, I'm not going to pass in just a reference to it. I'm just going to give it completely. And it might be even easier for me to use a full string. So like string from hello world. Then I can put this inside of a vector. So let my mutable my strings equals, do I have to, no, I shouldn't need to worry about anything. So let mutable my strings equals vec new. Then I'm going to push into it. So my strings dot push, and I'm going to put in, well, first of all, let's just put in our own one. So my number, like that. Now I want a block of text. So creating a block, I'm going to do something with my strings. Or maybe I put the block in here. So we create the vector in the block, we push it to in here. So now as soon as this block ends, the vector is going to be destroyed because it only has ever existed inside of this scope. But is my number accessible? My guess is no, because I think we've given ownership to my strings. So the best way for us to test that is just to print and say my number here. Will this allow us to do it, or will it say, hey, that doesn't exist anymore? Use of moved value my number. So we did give ownership. We moved the value of my number into the vector. So what we could do is borrow it. So instead of just giving my number, we can give it a borrow of my number. Then we could already see this error has gone away. And now we get to see hello world back here. So that's nice to verify that a vector will own it. Like we'll give ownership to it, even though it's just a data structure. So I think the biggest thing to put in here is to say vectors will take ownership of whatever is put inside them. Therefore, if you want to keep ownership, borrow it. Borrow the value, variable, thing, and then give it to the vector. Okay, so I think that's good here. Reading elements of vectors. Now that you know how to create, update, and destroy vectors, Knowing how to read their contents is a good next step. There are two ways to reference a value stored in a vector. In the examples, we've annotated the types of the values that are returned from these functions for extra clarity. Listing 8.5 shows both methods of accessing a value in a vector, either with indexing syntax or the get method. So let v equals vec. This is the macro, creating 1, 2, 3, 4, 5. Let third. So third is type i32 equals, that's a reference to vector position. Is that position 2? So it's 0, 1, 2. That's why it's third. Let third, and then we're going to put this, so option, we remember options from the enums. So type i32 equals v.get. So the two different ways of like grabbing this data. So we can go after it automatically, or we can use get, but clearly it's going to pass in an option for this, which we know can be a sum, like sum thing, or none. Note the two details here. First, we use the index value of 2 to get the third element. Vectors are indexed by number, starting at 0. Second, the two different ways to get the third element are by using the ampersand, which is a reference, and square bracket, which gives us a reference, or by using the get method, with the index passed as an argument, which gives us an option type. The reason Rust has two ways to reference an element is so you can choose how the program behaves when you try to use an index value that the vector doesn't have an element for. As an example, let's see what a program will do if it has a vector that holds 5 elements and then tries to access an element at index 100, as shown here. So let's try this ourselves and sort of like see how things are done here. So I'm also gonna get rid of that. Okay, so we want to create a vector. So we're gonna say let my vector equals vec. Oh, I was thinking that maybe it was gonna auto figure out what I wanted to have here. 1, 2, 3, 4, 5. We will then want to access this, so let third equals, and it's going to be a reference to position 2. Oh no, position 100. So does not exist 1. So okay, we're going to get that, and then let does not exist 2. Do I have to give it the type annotation of an option, or will that figure it out? So can I say my vector dot get position 100? Unused variable for both of these. That's not a bad thing. All right, so let's then try to print, and my guess is let's do each one here, and we're gonna have does not exist 1, does not exist 2, and my guess is it's gonna completely get a runtime error because this doesn't exist. Whereas this one is just gonna pass in none into the option type. And I think I read that like we do need to annotate that. So I should get an error saying like we didn't annotate it either. Okay, so on line 26, so that's this one, our print. Integer 1 doesn't implement standard format display. Okay, so that does not exist 1. Let's change those to the debug mode. And retry. Unused variable, unused variable. We get 100. Okay, I don't think I followed the instructions correctly here. Ampersand vector 2. Isn't that what I did? Oh, ampersand my vector. That was silly of me. Of course it got what it thought it was. Let's try this again. Unused variable, that's fine. Thread main panicked at index out of bounds. The length is 5, but the index is 100. Okay, so that's exactly the sort of problem is, and the compiler can't figure this out because a vector can grow that big. So it could potentially be there, so the compiler's not going to yell at me. So there's this problem. I'm going to comment that out, so that way we get past it. Cargo run, cannot find value, does not exist in this scope. Right, we need to also remove you. Cargo run. Okay, so unused variable, and then we got none because it doesn't exist. It passed that in. Oh, my preview window disappeared. Make sure. No drop frames, so I should be good. Also bring that back up. All right. When you run this code, the first square bracket method will cause a panic because it references a non-existing element. This method is best used when you want your program to consider an attempt to access an element past the end of the vector to be a fatal error that crashes the program. Which it does, but it does it at runtime. When the get method is passed, an index that is outside the when a get method is passed an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector happens occasionally under normal circumstances. Your code will then have logic to handle having either some element or none, as discussed in Chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none value, you could tell the user how many items are in a current vector and give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. And this is where we can use that let of or let for. Is it the let of? It was the if let syntax, where we can say like, hey, if this option type has something in it, put it into this variable. Otherwise, run this else code. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules covered in Chapter 4 to ensure this reference and any other references to the contents of the vector remain valid. Recall the rule that states we can't have mutable and immutable references in the same scope. That rule applies in listing 8.7, where we would hold an immutable reference to the first element in a vector and try to add an element to the end, which won't work. Okay, so let mut v equals vector this, let first equals 0, v dot push 6. We hold an immutable reference to the first element, which is first. or we're getting a reference to the first, where we hold an immutable reference to the first. Okay. The first element and try to add an element to the end, which won't work. But we did borrow v, so cannot borrow v as mutable because it is also borrowed as immutable. Interesting. Even though we're only borrowing a spot in it, we're not. So does this mean we're not actually getting the value of it? We're getting a piece of the vector itself. So we're not really getting the value. That's a bit interesting. So does that mean if we come back to our code here, in here we have our number and we give it ownership to, like we move it to the vector. Now if we have another thing here, so if we say like let mute another string, and we then pull this out. So what are you yelling about? Don't worry, you'll figure out the type very shortly. Another string is now going to equal. So, I mean, I guess I could borrow. So I could borrow my strings position 0. Variable another string assigned to but never used, that's fine. This is my strings does not live long enough because I'm borrowing it. So can I not borrow it? Can I just take it permanently? Yes, I can. And so now I can print this, and instead of my number, it can now be another string. Variable to, oh right, I remember someone told me this. I don't need mute if I'm not assigning it something right away. Okay, so this is one way to do it, is I'm just not using a reference. So I'm pulling it out and I get ownership of it. Can I also in here now print out the string? So print line, I think it's going to be my strings dot length. Is it just like that? Field length of construct vector is private. A method length also exists. Perhaps you wish to call it. Okay, so let's call the getter. So let's find out. So after we do this, it should be length 0, or is it length 1 still? But this, it has now sort of like a dead value because it's been given, like it's been moved out, so it cannot be really used anymore. Let's try it. Cargo run. So length of 1. So it still has the thing in there. Our hello world works now. So what we learned from this is that we can take it out and not just borrow it. Okay, where were we? The code in listing 8.7 might look like it should work, which is this one. Why should a reference to the first element care about what changes at the end of the vector? The reason behind this error is due to the way vectors work. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements to new space if there isn't enough room to put all the elements right next to each other where the new vector was, where the old vector was. In that case, the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent programs from ending up in that situation. Well, and that's true because for these borrowed values in memory, it's just passing it a location to where that piece in memory starts. But it's not like it's going to find, like in runtime, it's not going to go find all of the places where it's put that and then update the memory. That would be pretty crazy. It would be interesting, but I doubt that it's going to do that. Iterating over the values in a vector. If we want to access each element in a vector in turn, we can iterate through all of the elements rather than use indexes to access one at a time. Listing 8.8 shows how to use a for loop to get immutable references to each element in a vector of i32 values and print them out. Okay, so if we want to access each element, we can iterate. All right, so let v equals vector. So we have a vector between, with these three values. For I in the reference to the vector, print line. So we just immutably borrow the value in the vector. It's in this block, so that will get destroyed as soon as we're done, but the vector will be fine. And then we can print line here. All right, so let's do that really quickly. I feel like I changed this and I want to change my annotations before I forget. So take ownership. However, we can also take back ownership if we want to. The length is unchanged. The value at position 0 is no longer valid. Okay, so we have all this. Let's move down and do some iterations. So we have this vector right here, my vector. So let's iterate through that. So we're going to say for, it was like, I don't have to do anything in front of here. It's just I'm going to borrow here. I don't want to take ownership because that would be silly inside of a for loop. So for value in a reference to my vector, then we can print line, for example. So print line, and we'll just put in value. So we'll save that. Let's run it. And we get, 1, 2, 3, 4, 5. So exactly kind of like as we expected that would be. So that's easy enough. We can iterate over all values in a vector easily. It would also be nice if I turn that into a comment. We can also iterate over mutable references to each element in a mutable vector in order to make changes to all the elements. The for loop in listing 8.9 will add 50 to each element. So let mute v. So we create a mutable vector for I in, and then we borrow mutably this vector. We have to dereference the I. So that's, I'm still sort of like getting used to the asterisk. We're dereferencing the I, so that way we can add 50 to the value directly. To change the value that the mutable references refers to, we have to use the dereference operator, asterisk, to get to the value in I before we can use the plus equals operator. All right, because otherwise we don't really have the value. We have that sort of thing that points towards the value. And Rust will like figure it out what we want to do if we want to print it or something. But if we really want to manipulate it directly, we have to dereference it. Okay, so this is probably nice too. Let's see. Do I have any mutable vectors? Oh, only in here. That's not helpful. Okay, so we can also loop over a vector and change its values if it is mutable. Okay, so let's create a new vector. So we'll just say let nums equals vec, so 0, 1, 2. And then we want to, we need to also let mute nums. We need to loop over this. So for, it's going to be num in reference mute nums. Then inside of here, we dereference num. And now we can do our plus equals, and we can say, so num plus equals like 10. And then we can now print line. We'll give it the debug mode and nums. So now we should have like 10, 11, 12. So save that. Let's run it. Yep, and here's our 10, 11, 12. So perfect. We can go over it. All right, using an enum to store multiple types. At the beginning of this chapter, we said that vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need to store elements of a different type in a vector, we can define and use an enum. For example, let's say we want to get values from a row in a spreadsheet where some of the columns in the row contain integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different value types, and then all the enum variants will be considered the same type of that of the enum. Then we can create a vector that holds that enum, and so ultimately holds different types. We've demonstrated this in listing 810. So okay, we have enum spreadsheet cell int i32. So it can be an integer, it can be a float, or it can be some text. All right, so then let row equals, so here's our vector, and it's going to store 3 things, or at least this first. It's a vector that holds 3 things. So spreadsheet cell int 3. Then we have text string from blue. Okay, so that's what the text is going to be. So it holds that. And spreadsheet cell float 10.12. So 3 sort of like random things, but they're all inside of this type. So that's why they can hang out there. The reason Rust needs to know what types will be in a vector at compile time is that it knows exactly how much memory on the heap will be needed to store each element. A secondary advantage is that we can be explicit about what types are allowed in this vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that we always handle every possible case, as discussed in Chapter 6. If you don't know the exhaustive set of types the program will get at runtime to store in a vector when you're writing a program, the enum technique won't work. Instead, you can use a trait object, which we'll cover in Chapter 17. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vect by the standard library. For example, in addition to push, a pop method removes and returns the last element. Let's move on to the next collection type, string. Okay, so it removes it, it's like the length is gonna be smaller. Like that's what I'm saying. That's what I'm hearing. And I think like after we go through the book, then we'll like start building some random things in here, and that's when like the secondary learning part of this really happens, because as I built something, I was like, I want to do this. And the answer usually is, oh, Rust can do that. You just need to like figure out how. So if I want to pop something off, like let's say we have this length here, length is unchanged, we can pop it. So by saying my strings dot pop, and we can temporarily put you down here. I'm not going to keep this in the final version. I just want to see that this number goes from 1 to 0. And it is 0 now. Also, what's interesting is that it didn't yell. Yeah, it didn't yell at me, so it doesn't care that I'm not catching that variable. It's perfectly happy with me doing this. So I'm going to move you back. Don't need you. All right, so keep you going. Let's come back here. We're at the end of this section of the book, so let's continue on. Strings store UTF-8 encoded text. We talked about strings in Chapter 4, but we'll look at them in more depth now. New rustaceans, and I just realized I got a. New rustaceans commonly get stuck on strings due to a combination of three concepts: Rust's propensity for exposing possible errors, strings being a more complicated data structure than many programmers give them credit for, and UTF-8. These concepts combine in a way that can seem difficult when you're coming from other programming languages. Also, I want to make sure that I'm not dropping frames. I look like, yeah, I'm still alive. I'm going to see what, because that was Danny Fritz, who has communicated with us via comments before. I want to see if it was something about. Nope, it was just something about machine learning, which is fun too. Okay, so these concepts combine in a way that can seem difficult when you're coming from other programming languages. This discussion of strings is in the collections chapter because strings are implemented as a collection of bytes, plus some methods to provide useful functionality when those bytes are interpreted as text. In this section, we'll talk about the operations on string that every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which string is different than the other collections, namely how indexing into a string is complicated by the differences between how people and computers interpret string data. What is a string? We'll first define what we mean by the term string. Rust has only one string type in the core language, which is the string slice, stir. So interesting. So that's the only string type. I didn't even finish the sentence. Which is the string slice stir that is usually seen as borrowed form ampersand stir. In chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored elsewhere. String literals, for example, are stored in the binary output of the program and are therefore string slices. The string type is provided in Rust's standard library rather than coded into the core language and is a growable, mutable, owned UTF-8 encoded string type. When Rustaceans refer to strings in Rust, they usually mean the string and the string slice ampersand str types, not just one of those types. Although this section is largely about string, both types are used heavily in Rust standard library, and both string and string slices are UTF-8 encoded. Rust standard library also includes a number of other string types, such as OS string, OS stir, C string, and C stir. Library crates can provide even more options for storing string data. Similar to the is that dereferenced string stir naming, they often provide an owned and borrowed variant, just like string and borrowed stir. These string types can store text in different encodings or be represented in memory in a different way. For example, we won't discuss these other string types in this chapter. See their API documentation for more about how to use them and when each is appropriate. Okay, so creating a new string. Many of the same operations available with vec_t are available with string as well, starting with a new function to create a string shown in listing 811. Let mutable s equals string new. I think, yeah, we've seen that. This line creates a new empty string called s that we can then load data into. Often we'll have some initial data that we want to start the string with. For that, we use the toString method, which is available on any type that implements the display trait, which string literals do. Listing 812 shows two examples. So let data equals, and then this is the initial contents. Now, if I remember, this comes in as a stir. So let s equals data dot toString. So we're converting the stir to a string. And then this one is let s equals, and then just a literal, and then followed by toString. This code creates a string containing initial contents. We can also use the function string from to create a string from a string literal. The code in listing 813 is equivalent to the code from listing 812 that uses toString, which is both of them. So that okay, so the string from, right, and that's what we learned way long time back in like chapter 3. Because strings are used for so many things, we can use many different generic APIs for strings. Providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string from and toString do the same thing, so which you choose is a matter of style. Remember that strings are UTF-8 encoded, so we can include any properly encoded data in them, as shown in listing 814. Okay, so just all the different languages. All of these are valid string values. Updating a string. A string can grow in size and its contents can change, just like the contents of a vector type, by pushing more data into it. In addition, we can conveniently use the plus operator or the format macro to concatenate string values together. Oh, I was just getting happy that I was getting away from that with JavaScript. I am not a personal fan of the plus operator being used with non-numbers. Oh man, okay. All right, fine. However, it is 7:50. Looks like we're coming to a section that we're going to experiment with code. So I think what I'm going to do is not go through this yet, but let's go ahead and update what we have, and then get this pushed up to the repo. So, is there anything we want to change in here? I don't think so right now. So in main, we'll just say like added vector examples from the book. I'm not going to push this up right now because we have some more changes coming in. So we can close this up. We're now going to be in chapter 8.2. So let's go find this. And we're going to vim the README. So 8.2, and appending a string with a push string and push. Ooh, it didn't like that because it thinks that it wants me to like, because it's markdown, it thinks that I'm trying to like italicize something. So that, quit out of here. Okay, so AM, so that we also have this README here. For this README, we're updating where we are. And I'm gonna go ahead and push up all these changes. So this Learning Rust repo that I have, it is on GitHub. I have the link to that repo in the description of the stream and also the VOD. So if you want to follow along, sort of see what I added today, or just like read the book while listening, I have those examples up on GitHub. Other things. It looks like we're going to be getting into interesting things here coming up soon. After that, I think like things are looking good with Rust. I'm not like completely pleased that we're about to get into like the plus operator, as it feels like it's going to be overloaded. So it's like plus for numbers, which adds them together, and then with strings, it concatenates them together, which is one of the things that was super happy in JavaScript to get away from with the string template literals with ES 2015. But I'll hold off like too much judgment until I see them and sort of like decide how I feel. Those are just my initial like gut feelings upon hearing that. Besides that, I sort of like starting to come up with like different ideas of what types of projects that we can build. Like, because these chapters are sort of like introducing one specific thing at a time, it's kind of feeling a little bit difficult to decide if there's a project that I can work on, like right now, and what that project would be in order to limit its scope to the things that I know. If any of you know of anything or have any suggestions, like for example, the temperature converter type stuff, please leave a message, like leave either an issue on the Learning Rust, or just leave a comment on the YouTube video. with that being said, I think it would also be fun to do something like that, and maybe like, you know, get somebody in the stream with me, and we can do a pair programming exercise, building one of those things up. And if it's me, if it's the person I bring in who knows more about Rust, I'll make them navigate and I'll drive, so I can get some good learning with that. All right, but with that, as I mentioned yesterday, we're going to finish this week's streaming here on YouTube, and next week I'll be streaming on twitch.tv on my channel there. I will be tweeting out and putting into the description where you can find that channel on Friday or this weekend. Anyways, don't worry about going there right now. I just want to give a heads up that next week the videos will be initially streamed there and then archived over here to YouTube. And with that, I don't have anything else. So thank you for stopping by and watching. Thank you for watching the VOD, and I hope that you have a great day.